Welcome to Semester 6 Financial Statistics. Today we are diving into one of the most fascinating and foundational concepts in modern quantitative finance, Brownian motion. Whether you realize it or not, the unpredictable, jittery movements of the stock market can be modeled using the exact same mathematics that physicists use to describe floating dust particles. By the end of this lecture, you will understand how we tame this wild randomness to price complex financial derivatives. Let us get started. Now that we know what we are studying, let us look at where this idea comes from. Imagine watching a tiny speck of dust floating in a sunbeam. It jerks around randomly, constantly colliding with invisible air molecules. You can never perfectly predict its next move. In finance, we use this exact physical inspiration to model stock prices. Just like the dust particle, a stock price is pushed up and down by invisible market forces, news events, and trader decisions. Mathematically, we call this a continuous time stochastic process, often denoted by the letter W, named after Norbert Wiener. It is a collection of random variables changing over time. To actually use this stochastic process in mathematics, it must follow strict rules. There are 4 defining properties of a standard Brownian motion. First, it always starts at exactly 0. We begin observing before any randomness happens. Second, it has independent increments. This means the change in a stock price tomorrow is completely unaffected by the change today. The market has no memory. Third, the change over any time interval follows a normal distribution, meaning the spread of possible prices grows as time passes. Finally, the path is continuous everywhere but differentiable nowhere. It has no teleporting jumps, but it is so infinitely jagged that you can never draw a smooth tangent line to find a slope. Now that we understand the 4 properties, let us look at the mathematical formula for the third property, the normal distribution of increments. The term W of t minus W of s represents the change in the process between an earlier time s and a later time t. The tilde symbol means is distributed as, and n stands for the normal distribution. The first parameter is 0, which is the mean. This tells us we expect the price to go up just as often as it goes down. The second parameter is t minus s, which is the variance. Notice that the variance is exactly equal to the time elapsed. As the time gap increases, the variance increases, meaning the future becomes much harder to predict. Before we move on, let us see this with a concrete visual example. What you are looking at is a simulated path of a standard Brownian motion. On the horizontal axis, we have time, and on the vertical axis, we have the value of the process. Notice how it starts exactly at the origin, 0, 0, satisfying our first property. As time moves forward, the path wanders up and down. Look closely at the line itself. It is continuous, meaning there are no breaks or gaps. However, it is incredibly jagged and sharp at every single point. This perfectly illustrates what we mean by differentiable nowhere. The longer we wait, the further the path can potentially wander from the 0 line, visually confirming that variance grows with time. Now that we have our formula and visual intuition, let us apply it to a real calculation. Suppose a financial asset's random fluctuations are modeled by a standard Brownian motion. It starts at 0, and we want to find the probability that the asset's value is strictly greater than 2 after exactly 4 years have passed. This is exactly how we determine if an option might expire in the money. We know the value at year 4 follows a normal distribution with a mean of 0 and a variance equal to the time elapsed, which is 4. To find probabilities, we first need the standard deviation. By taking the square root of our variance 4, we find that the standard deviation is exactly 2. This is the typical distance the asset might wander. Continuing with our calculation, we now use this standard deviation to find our probability. We use the standard z-score formula from basic statistics, which is our target value minus the mean divided by the standard deviation. We substitute our specific numbers. Our target value is 2, the mean is 0, and the standard deviation is 2. This gives a z-score of exactly 1. This means our target value is exactly 1 standard deviation above the expected average. Finally, we look for the probability that our standard normal variable z is greater than 1. Looking this up in a standard normal distribution table, we find the probability is approximately 0.1587. So there is roughly a 15.87% chance the asset will be worth more than 2 after 4 years. We have successfully calculated probabilities, which brings us to a deeply fascinating and strange feature of Brownian motion called quadratic variation. In standard calculus, if you take a tiny change in time and square it, the result is so incredibly small that it effectively becomes 0. However, Brownian motion is different. Because its path is so violently jagged, if you measure all the tiny squared changes along its path and add them up, they do not shrink to 0. Instead, they accumulate to a perfectly predictable solid number. Even though the path itself is completely random and unpredictable, its squared volatility is perfectly deterministic. This predictable nature of the variance is the foundational bedrock that allows us to price options accurately. Now let us look at the mathematical representation of this concept. This is the differential form of the quadratic variation rule, and it is arguably the most important equation in all of stochastic calculus. The term dw represents an infinitesimally small change in the Brownian motion, and dt represents an infinitesimally small step forward in time. In normal calculus, squaring a tiny change gives 0. But here, squaring the random change dw gives exactly the time step dt. This rule is the absolute key to Ito calculus, which is the special branch of mathematics used to handle random processes. Simply put, it tells us a profound truth. Randomness squared equals time. Let us explore another example to see how these properties interact, specifically focusing on variance. We want to calculate the variance of the sum of two overlapping time periods, the value at year 2 plus the value at year 5. This tests our understanding of how past events are embedded in future values. We cannot simply add the variances of W of 2 and W of 5. Why? Because they are not independent. The value at year 5 already contains the journey up to year 2 within it. To solve this, we must rewrite W of 5 by breaking it into two independent pieces. The value achieved by year 2 plus the change that occurred between year 2 and year 5. Continuing with our setup, we now substitute our broken down version of W of 5 back into our original expression. We get W of 2 plus another W of 2 plus the independent increment from year 2 to year 5. We simply combine the like terms, giving us 2 times the value at year 2 plus the change between year 2 and year 5. Because these two components are now completely independent of each other, we can safely apply the standard rules of variance. Remember, when you multiply a random variable by a constant, like 2, its variance is multiplied by that constant squared, which is 4. And the variance of the sum of independent variables is just the sum of their individual variances. Now for the final calculation. We know from the properties of Brownian motion that the variance of W of 2 is simply the time elapsed, which is 2. The variance of the increment from year 2 to year 5 is the time difference, which is 3. We substitute these values into our equation. Multiplying 4 by 2 gives 8 and adding the increment variance of 3 gives a final total variance of 11. This result perfectly demonstrates how the shared history of the process increases the overall uncertainty. By breaking the timeline into independent chunks, we can accurately measure risk over overlapping periods. Now that we have worked through the mathematics, let us zoom out and look at why this matters. Brownian motion is the absolute foundation of modern financial mathematics. Without it, the entire field of quantitative finance would collapse. It is the primary tool used to model the random behavior of stock prices, interest rates, and exchange rates over time. The famous Black-Scholes formula, which is used globally to price options and manage risk, relies entirely on the assumption that stock prices follow a variation of Brownian motion. By understanding the predictable variance hidden inside this random movement, banks and traders can calculate fair prices for complex financial contracts and protect themselves against catastrophic market crashes. We have covered a lot of ground today, so let us review the key takeaways. First, Brownian motion is a powerful mathematical model for continuous, unpredictable randomness, perfectly suited for financial markets. Second, remember its core properties. It has independent increments and its changes follow a normal distribution, where variance equals time. Third, while its path is infinitely jagged and impossible to forecast, its squared variations accumulate in a perfectly predictable, deterministic way. This unique blend of wild randomness and strict mathematical structure makes it the perfect tool for modeling finance. You have now taken your first crucial step towards understanding advanced stochastic calculus. Great job today!